Okay, hello everybody. It is 11 o'clock on the dot. This is the contributed orals session. If you don't want to be here, then feel free to leave right now, but that's where you are at this very moment. My name is Kit. I'll be moderating this session, and Jillian Goodwin will be moderating online and the timekeeper. So just a couple of reminders. We do have a handy-dandy little light system up here. You have 10 minutes for talks, 3 minutes for questions, and 2 minutes to switch over. If you go over your 10 minutes for talks, that'll just eat into your question time. But if you do start to approach that 13-minute mark, we will have to ask you to wrap up so the next person can talk. Additionally, I'd like to make sure that we thank all of our Diamond sponsors. Without their support, it'd be a little bit harder to run a meeting, so yay for them. And if you have any questions, please feel free to ask them before we get started. But if you feel comfortable with how things are going, we'll go ahead and get started. Cool. So I will introduce myself. Hello, I am Kit. I am the first speaker, and I will migrate to the podium now. Okay, awesome. So I will go ahead and precursor this with, I have a lot to talk about, and I'm gonna go kind of fast, so please feel free to ask me questions afterwards. But I will be discussing the NASA Bioscape airborne campaign, and mainly what I'm doing with it is hyperspectral multi-scale imagery to understand biodiversity and to also map invasive species on the Cape in South Africa. We have quite a few collaborators in this project, and I'll give a quick overview to what Bioscape is. This is NASA's first biodiversity field campaign, and it incorporates airborne imaging, spectroscopy, so lots of different light bands, LIDAR, and field observations. So this is happening in the green portions on the map in South Africa. And our main thing that we are looking at is fynbos vegetation. So the area that we are looking at is one of the world's 35 biodiversity hotspots, and it's estimated that 69% of the plants of the 9,000 plant species are endemic, and it is a protected UNESCO World Heritage Site. It does only make up 4% of South Africa's landmass. However, 67% of the country's threatened taxa are here in this 4% area. So once again, that is the area that we are looking at. So this is an Old Dutch word for fine bush, and a very healthy grassland has multiple of these, and they're very specialized to being able to grow in nutrient deficient soil, so the type of stuff that you would find on the Cape. So they are also kind of small, and we're having an issue where invasive species are coming onto this grassland. So pine, acacia, and eucalyptus trees are taking over areas of the Cape, which has some pretty serious impacts for fire loads. So like I said, the fynbos bush is like kind of small, not very large, very well adapted for the climate. Unfortunately, also these invasive tree species are very well adapted for low nutrient soil too. And where that becomes an issue is they're replacing native plant diversity and impacting water, the water table. And on top of there being less groundwater for moisture in the environment, they're also increasing fuel loads of up to 25 times. So we're seeing some pretty devastating fires, and fire regime is becoming faster and more intense in this area. So what we are trying to do on the invasive species team is use a multi-scale imagery approach where we take ground observations, and our middle observations are in the sky. If you've ever heard of NEON, or the National Ecological Observatory Network in the US, it is the same hyperspectral platform, but we've also added in more spectrometry ranges to really focus on infrared, shortwave infrared, thermal emissions, and LIDAR to look at structural point cloud diversity. So once again, I already kind of said this, but the main goal of this campaign, it's 19 projects. I'm on one of the 19 projects. We want to know how we can monitor biodiversity from space. And how a lot of that is being done is we are just scaling up and scaling up and scaling up imagery to get information about individual pixels as they go up. So down on the ground, we're taking collections, vouchered specimens, pictures, observations, on the ground hyperspectral readings of what plants are. And then our next level that we go up is that ABRIS imagery right here, where we can get down to between 5 to 6 meters per pixel resolution and extrapolate information from that. And then for us, we're trying to go on a much bigger scale so we can look at older imagery. We are scaling up our ABRIS imagery into MODIS pixels, which are 250 by 250 meters, in order to see how communities are being impacted. And the way that we are doing that currently, we're running into a couple of things where we might have to make an extension, but we are using something called the La Liberté algorithm, which takes information. This is an RGB photograph, so that's only 3 bands. We are using it for hyperspectral imagery, which is 426 bands minus a couple for atmospheric corrections, and running a principal component analysis to pull out specific information. This one shows 3 bands, and all of my examples will show it down to 3 principal components. But right now we are looking at scaling that up to 12 to 15 principal components. And from that, we section out our 250 meter regions. So this is not related to MODIS at the moment, but we are sectioning out 250 by 250 regions to then make communities within those 250 by 250 meter regions to look at alpha and beta diversity. So gamma diversity is all of this. So all of the colorful things, it's looking at each pixel and how diverse it is to the other pixels in there. Alpha diversity looks at how diverse a single 10 by 10 area is, so a smaller community. And beta diversity looks at how different are the communities from each other. So the reason we are looking at that is we have a hypothesis, and this is just another different way of explaining that. We have a hypothesis that depending on the diversity metric and how diverse it is, that might make it more open for invasion and invasive species to come in, and being able to extrapolate that from space. So once again, airborne scale to our community scale to our regional scale. More of the same thing. So, and just for a little bit more background, so beta and alpha, you can see that all of these different communities that have multiple pixels in them are very different from each other. So that would be high beta diversity, but within the actual communities, they're very similar. So that would be low alpha diversity. And then the flip side of that is the communities are very similar to each other, but very diverse within one another. So like I said, kind of confusing. Please feel free to ask me questions. So what I have done so far on this project is I've made a modular methods pipeline where anybody can slot in their information based on where it is, where I scrape data from the NASA servers. So even if you don't have access to the SMCE or the NASA computing cluster, you can actually access this data. Mosaic the data together after doing some atmospheric corrections, isolate certain spectral ranges that I want to see, and that would be the red bands and the near infrared bands, to isolate those to run an NDVI or a normalized vegetation index to see what plants are healthy and what aren't plant pixels, because if it's not a plant pixel, I'm not quite as concerned with it because there's quite a few roads. It's a very mixed environment that we're looking at. Segment those into those 50 by 50 pixel communities that you were looking at because it is 5 meters, so 50 by 50 pixels is 250 by 250 meters, and then segmenting those into 10 by 10 pixel subcommunities to get the alpha and beta diversity. So my first job was finding some of our test sites. I just scraped this. These are pictures of our flight lines. Much like photogrammetry with specimens, we have overlap that we have to do in order to make sure that we get enough data. So I just scraped that using a Python script. There should be a picture of that there. So this is a very blank slide. But it will scrape either all the files that you want, or you can put in a shape file and get the specific file names that you want. It's very flexible. Or if you have access to the NASA SMCE, we have an S3 bucket that you can pull all of that from. So the first thing that I did, like I said, got normalized vegetation index. This is just a grayscale photo. And most times when you do an NDVI, you want to look at things above 0.8, so like 80% healthy vegetation. Due to the way that NDVI works, it's isolating out chlorophyll, and a lot of our plants don't have like a bunch of chlorophyll. So we put that down to 0.35, made a mask. So where you see all of the black pixels here, that's the only information that I'm interested in. I take that mask and put it into my whole hyperspectral imagery and run this principal component analysis. Like I said, this is for 3 components, but we are looking at more, and it will do a flexible output where you can use enterprise or open source formats with header files, binary files, JPEG, and or TIFF and GeoTIFF if you want to use that. Then I segment out our average pixels. This is just one 50 by 50 pixel community, and send that over into alpha diversity to see what is the most diverse and what is the least diverse. And we'll be going through this. It comes out in like a big CSV file, and then we go through that data. And our future work is we'll be doing full spectrum analysis, which I hope my computer doesn't explode. And then we'll be doing structural diversity, looking at LiDAR and waveform and canopy modeling of these areas. And the next big thing that I thought would be like super simple, but it's not, is we'll be doing MODIS pixel projections. So that is where we'll actually project our average imagery into the format that MODIS is, and then get like actual data going across to look at MODIS. So we'll be using this to map ecosystem functions, water use efficiency, and look at the fuel loads. And that is something that we'll be starting on in probably about 2 weeks. And other future work that I would really love to see is the introduction of drone photogrammetry as another layer, because I said that each average pixel is 5 by 5 meters resolution. This is some missions that I've flown around Colorado. And you can see that I can get a lot of these down to, depending on how high I'm flying and how much overlap I have, all the way down to 1.85 centimeters per pixel, which is really great for training models to have that amount of data. And just for reference, I tried to get it as close as I could. In that 5 by 5 meter pixel here, that would just all be one color. Like it would just be one piece of information. And then if you use satellite imagery, MODIS is much larger than this. But Landsat is something that people use a lot. This would be 1 pixel, like 1 color on Landsat. So I'd love to acknowledge my wonderful team. Oh, and I want to make sure to acknowledge Megan Hayden, who I did not put in here, but Megan has been extremely important to helping me with this, and we've been working on the structural and invasive species maps and hyperspectral data together. So thank you. Feel free to ask any questions. I have time for like 2. So.
Hi, it's a great talk. I loved it. Have you used the photogrammetry stuff that you showed at the end to develop some uncertainty values for the larger area pixels?
So we haven't done that yet. That's kind of next on the docket. So a couple of things that we're looking at is spectral and mixing too. And looking at uncertainty metrics, and especially for the NDVI, you've probably noticed that there were a lot of like blanks. I'm looking into rarefaction in order to still be able to use that community value, and but have the data that we need. So does that answer your question? Okay. Okay. Are there any online? Perfect. So I'm going to grab my computer to introduce the next person. Okay, awesome. Thank you again for listening to me. Our next speaker is Ed Baker from the Natural History Museum in London, and he will be talking about bioacoustic and ecoacoustic data and audiovisual core.
Hi.
Take it away.
Yeah. Yep, so I'm the acoustic biology researcher at the museum, and I'm also the convener of the audiovisual core maintenance group for TDWG. Oh, yeah. You got it. So very quick run through of bioacoustics, ecoacoustics, and the difference. So bioacoustics, traditionally, at least in our sense, is quite akin to like specimen biology. So some things from our collection, the orange labels are things we've got sound recordings for. We also have some metadata about these sound recordings and lots of magnetic tapes. And this is kind of what we have. So we have some sound recordings, and there's different parts to them. So there's some metadata, the voice introduction, some bits which have got lots of noise, and also some nice clean recordings of species calling. And this kind of stuff I do quite a lot of the time. It's like looking into quite good detail about song structure. But the basic thing, repeated from the last time, is like we're looking at time segments. So these are all like little segments of time which are important to calls. I don't need to worry about it now, it comes up later. If you're really interested in our acoustic work, we have a nice URL there with a cricket in. It's got some examples of our research based on our sound collection. And ecoacoustics is, so this is like traditional, this is actually our old recording studio at the museum. And ecoacoustics kind of really came about when computational power became cheap, small, pretty much the case where it's almost disposable, right? We don't care too much if one of these is lost, damaged, or stolen. And it's moving from looking at individuals in quite a narrow sense to like ecology, landscapes. We also tend to use this like slightly different construct for analyzing it. So instead of looking at a pure time series, we've got frequency going up on the y-axis here in time. But you can start to see we're doing the same kind of thing even in this analysis. It's kind of like bounded time regions, but also with some bounded frequency regions. So some just quick examples of what we're doing in ecoacoustics work. This is our citizen science project, which is looking at insects and road noise. We have all of these sites, our partner sites across the UK, with AudioMOS, which are tiny little battery-powered sound recorders. And in our new museum gardens, please do come and visit. We've got like this hardwired data network with lots of sensors. And it's kind of important to think of acoustics not just as what we hear, but the other environments where sound is. So fresh water, our ponds, really, really noisy. Soil is becoming quite an active area of acoustics research, so all the things moving around in soil. Listening inside timber, so like living trees, you can hear water rushing up after periods of drought when it rains, or you can hear structural cracks in the timber starting to appear before like limb loss. Ultrasounds are like bats, but also quite a lot of crickets. And also like looking at spatial audio, so like arrays of microphones where we can get directionality from things. So we can go, this species is singing up here somewhere in this tree or down here in this bush. And then, so just go through how we start analyzing this stuff. So one of the things we do is we just take time windows and we just move them across, and we analyze what's in each like kind of window. And probably the best used example of this in acoustics is BirdNet, right? So it's Merlin, or the AI network behind that. So coming more towards audiovisual core, audio files can contain lots of things, right? They can contain many species, sometimes overlapping. Things which aren't species, like road noise, aeroplanes, people talking, the weather, all kind of have an impact on the soundscape. And these different parts can be used for different purposes. So like I'm an insect person, right? I work on Orthoptera. I go to a bioacoustics conference, and lots of what I work on is just called noise, right? Because people want to work on birds, and the constant din of a tropical forest, which I think is a really rich data source, to them is just an annoyance. And so people just tended to filter that out. So you put a high-pass filter on, you get rid of all of the insects you want, or you get rid of the road noise, or you get this thing. And actually, we don't really want to filter out other people's data. So we need to identify regions within files to do some analysis. And in like the broader audiovisual core thing, this is also important in other sections. So like if you're identifying regions within audio files, you want to do the same within, like say, images of herbarium sheets, sections within video. So if you've got videos of coral reef, you want to go, this fish is like here in this moving box like this. So the kind of main solution we came up with, which is like, it has been released in audiovisual core, but it is an ongoing thing which we are still working to develop, is regions of interest. And in the acoustic sense, they're defined by some time things. So we have two different time things. One is just the start and end time, which is relative to the file. So lots of our laboratory recordings, the actual time that was made is not particularly relevant, and it's just within the file. When you get into the broader ecoacoustic thing, actually the time of day is really important. Soundscapes shift dramatically throughout the day, throughout the year. And also these frequency boundaries of low and high frequencies. So we can, within audiovisual core, we can define a region of interest within a file. And from that, we can either just label it like this is a road noise, or we can build occurrence records linked to that. So we can start taking this whole soundscape and breaking it down into things which, different uses for different people. Just to keep the completeness, the x fraction, y fraction, these things, radius, this is the same thing in images. So you're saying there's a point this far into the image, and then a certain width of it, height, defines a box within an image, or like a circular radius region. So we can start like creating these regions, not just within audio files, within sound, within video. While I've been developing this, there's a few things we're doing. First is this demonstration service, like audioblast.org, which combines mine and some of my collaborators' data. So we're combining recordings, but we're also combining an awful lot of BirdNet identifications from our museum's research, Sounds of Norway projects in Borneo. And the other thing which comes into here is like a trait database. So it was part of a previous project when I was at University of York. We developed this massive acoustic trait database of Orthoptera. And that goes to show, like, so the current outputs of BirdNet just give you like this 3-second time region. But you can combine that with like a traits database to kind of narrow down that thing. So if you know the song of a certain animal is within a certain frequency bound, you can combine the identification and the database to get like 0 in, which gives you like, you can then filter out the noise and gives you a nice clear thing to either check or just listen to. And some things which are coming soon from Audiovisual Core, and thank you to the core team of Audiovisual Core. They've all been fantastic. One that's coming up is a content description controlled vocabulary, which we're putting into public comment period soon. And this is a controlled vocabulary which just labels these regions or files. So this would be like, is this a photo of a specimen? Is this a photo of a habitat? In the acoustic sense, is this the voice introduction, or is this actually the call of an animal? So that link there, if you want to comment on that or see what the proposed controlled vocabulary is. And also the 3D task group, who have been expanding lots of our work on media into like 3D objects or 3D reconstructions, which has been really important. And if you're interested, the Audiovisual Core GitHub thing has details of our maintenance group meetings, which are the third Wednesday of the month. And we try to put the agenda and topics we'll be discovering up before that happens. And I'll leave that there for now, before we get too far into the weeds.
Awesome, thank you. If there are any questions in the room, please feel free to come up to the microphone, and we will also be monitoring questions in the chat. Not a question, but I met one of your collaborators in Boulder. His name is Sam, and he's here at OIST.
I'm going to see him on Monday.
Yeah, so he talked about a lot of this too. It was super cool.
Can you elaborate on how you, on soils?
Soils.
Yes.
So soils, you just take a piezo microphone, just like contact microphone, or like even a hydrophone. And like soils are really complex acoustic environments. So in the air, there's like, at one time in the air, there's one speed of sound. But in soil, you get 3 speeds of sound, possibly, through the solid part, through the air part in the soil, through the liquid part, and they all reflect around. So it's a very dead sounding environment. But there's a lot of things happening. So every time something moves in soil, it makes an awful lot of noise, just disturbing the soil. But there's also things which do like deliberately make noise in soil. So there's all kinds of like beetle larvae which deliberately stridulate, either to find each other or when females are coming in to lay eggs, to kind of pull off, say that this resource is being used by these larvae already, don't lay your eggs here. So it's an exciting environment. It's quite hard to study. But.
Any other questions? Oh, we got one in the chat. We have a comment. It says, just watch magpies listening for movements.
Yeah.
Like in the soil, yeah.
Yeah.
Awesome. Well, we can go ahead and start moving on to our next talk. Thank you again. Let's give another big hand. So our next talk is being given by Francisco Pando, and it is Plinian Core, a data specification for species pages in the real world.
Good morning. Thank you very much, Kirsten. First, I introduce myself. I am Paco Pando. I'm based at the Royal Botanic Garden, Madrid, Spain, and then here as the convener of the Plinian Core task group. I start by saying that this is not my presentation, but the presentation of the core group of the development of Plinian Core. In past task group meetings, we have been focused on the most technical aspects of the data specification. In this occasion, we will focus on what is around the data specification. So I will start with a very short introduction of what is Plinian Core. Then we choose just 3 real-world cases to see what happens when you prepare a data specification and how that is used and manipulated. Then a little on lessons, some learned, some to be learned yet. And then I will finish with some aspects of how to police, exchanging, and downloading species-level information. And I will finish with some final reflections. So, Plinian Core in the landscape of the TDWG standards. There is a few data specifications dealing with species-level information, such as Delta or the structured descriptive language, and in that realm also plays a Plinian. Plinian Core is different from the others in the sense that it covers not just biological information, but also other aspects related to the species, such as legislation or uses or management. It reuses a number of terms from other standards, such as Darwin Core, Dublin Core, EOL, and some others. And with this, I move quickly into the real world cases. The first one is the Cross Nature project, which is a project to set up a Sparkle endpoint for the Ministry of for the Environmental Transition of Spain that uses Plinian Core as the basis for sharing and publishing information. And to highlight in this case, well, first is an official national repository for species-level information. And in the context of the project, a Sparkle endpoint was set up that allows to connect seamlessly species-level information from other repositories, such as the EA, the European Environmental Agency, and also the Portugal national access point to the species information. It went beyond the standard in one aspect as to set up individual identifiers for all the 10 per 10 square kilometers in the territory as to extract easily information about those areas. And also an ontology was developed for this case. The second case is the biodiversity catalog of Colombia, prepared by SIP Colombia, which is also the GBF node for Colombia. It is a very comprehensive catalog. It has information of over 6,000 species, with information on all aspects of these species, and uses what in Plinian Core, and I will go on this later, on the non-atomized items. And the third case is the Encyclopedia, which is also a national catalog of species set up by the Conavio in Mexico. It is a very large repository of information covering information of about 140,000 species. To highlight here is that it provides for each species two views, one for the general public and another one for the most specialized audience. And then a bit on the lessons learned. PLIANCORE has been around for a number of years now, and one of the tensions within the group was to which level to specify the information about the species. And the result was that for each piece of information, PLIANCORE provides two approaches, what we call the unstructured approach and the atomized approach. The unstructured approach basically set up a box of text on the concept, for instance, feeding or annual cycle or reproduction and so on. And then the atomized branch provides a number of specific terms to better define and to better manipulate and access that information. And depending on the case, some projects goes for the unstructured route, some others go for the atomized route. In many cases, it's a mixture of the two approaches depending on the focus of the project. And in some projects, as we saw in the Mexican case, uses both approaches, providing unstructured and atomized information for each piece of content, and also the Spanish case does the same. And for instance, here it provides a text on the distribution, but also provides all the individual temperature square kilometers. And the basic form or the most used form of PLIANCORE is in XML schema definition, and here we can see an aspect of the unstructured and atomized cases. Then, following the good practice, PLIANCORE reduces terms from, I believe, 5 or 6 other schemas. And the matter in this area is that those schemas have a life by themselves, they evolve, and basically to keep everything coherent and working together is like the Red Queen dilemma of Alice in Wonderland, that we have to change and track to follow and track all those changes to keep everything working. And in some cases, that was, so hard that we decided to have a local version of that schema from which we borrow the terms. Then another aspect of this linking schemas and reusing terms is, a few aspects here. First, we reused terms from standards in analog form. For instance, the economic botany. Basically, PLIANCORE in this area, which is species uses or plant uses, make a port into a digital form of the standard published by Francis Cook in the 90s from Q. And then, for instance, for the aspects dealing with invasive aspects of the invasive species, thank you. We use the GISIN schema, which is not longer in use, and then we have to deal besides with broken links and so on. Yes, approaching the end of the presentation, regarding publishing, exchanging, and downloading, we have in parallel developed extensions to work with the GBIF IPT tool. This is in test form, but we expect that as PLIANCORE approaches the public review, that will be available for anyone to produce Darwin Core archives using PLIANCORE terms. And then we are currently exploring and preparing other formats for data exchanging and downloading, such as the frictionless data package and the research objects crates as to a way to exchange and to deploy species information in PLIANCORE form. And then just to finish, to review a few other aspects. First, that species level information is more like a product than data for analyzing. And in that regard, the data aggregation occurs very little, and the emphasis is on discovery. Then all of these projects do their own developments, and some of them could be used to improve the standard, but the feedback doesn't occur. And third, there is quite a space between the data specification and using it. And in that aspect, also, these projects develop their own guides on how to use Brilliant Core. And with this, I finish my presentation, and I hope I have time for questions. Thank you.
Perfect. So if there are any questions, please feel free to come up and ask those at the mic. And do we have any questions online? Okay, cool. Well, we'll wait a couple of seconds. Okay, I mean, this is your only chance. You're just hurting yourself if you don't have any questions. Okay, thank you so much again for your talk. And our next talk is, oh, sorry, I lost my page. Give me 1 second. Okay. Our next talk is by Dmitry Dmitriev. This will be on history extended migration of Systema Dipitororum into TaxonWorks. Thank you.
Okay, hello everyone. I'm working with species file group, which is mostly located at University of Illinois, United States. We have a number of programmers, biologists. We also have a couple of people working with us in Argentina. We mostly focus our development in TaxonWorks and Taxon Pages, partner project for the public interfaces for the data in TaxonWorks. We also work on the development global names by Dima Margerian and Catalog of Life, mostly by Yuri Roskov and Jeff. Systema Dipterorum is an old database on diversity classification of order Diptera insects. It has 40 years history, originally designed by Christian Thompson as FileMaker database, and data entered by him, and after his retirement, now it's inherited by Neil Evenhuis and Thomas Pipe. Data shared with Catalog of Life, and through that to JBIF as well. We have a long discussion. I would have a disclaimer, it's still work in progress, so nothing is solid, but we have discussion about potential migration of data from FileMaker database into TaxonWorks. Some statistics, I borrowed slide from Thomas Pipe. It's large data set compared to other data sources coming to Catalog of Life. So 172 more now 1,000 valid species names and bibliographic reference about 40,000 data sources. It's mostly a nomenclatural checklist and bibliographical database. But what most interesting for me in this data set is number of nomenclatural and taxonomical statuses, 78 statuses used in the database associated with each name. And also verification codes they use in the system. The code basically calculated to say how complete is the record, was the record verified to the original source, etc., etc. And it ranges from 1 to, I believe, to 199. TaxonWorks. TaxonWorks is a platform. It's an open source. We are on GitHub. It's a platform for the wide range of biologists, collection managers, and other. We have a set of tools. System has modular structure to satisfy different needs of the people. And so, yeah, it's a number of tables. I wouldn't say much about this, but basically it means we can basically feed different kinds of data and make sure that we don't lose any information when we migrate from one database to another. Last time I checked, it was 80 projects in the production. We try to classify those a little bit. There are nomenclatural projects, mostly in blue, digitization or collection management projects in red, descriptive, it could be interactive keys for identification or other data, literature green, and geospatial. As you see, there is a variety of projects in the system. Standard interface, when you enter, you have a lot of cards, call those tasks, interacting with data. So you don't work with individual tables. Basically, a task brings the data from multiple tables and to better visualization of the data. Since it's mostly a nomenclatural database, this is browse nomenclature interface where data summarized about species, valid name, so list of the synonyms, bibliographic information, classification tree. One of the things we are proud of is a soft validation model, which basically enforces the rules of zoological nomenclature as well as botanical and nomenclature from other codes, giving you some suggestions what could be updated on the record, what is missing, and also it may fix certain things which could be fixed automatically. For example, you have genus and subgenus. It's supposed to be having the same type species, same author and year. If one of them have this information and another missing, we basically can enhance data with this information automatically. Another important aspect, our annotation system. This radial button opens annotation menu, and we can annotate virtually any object in the database with a variety of different kinds of data. So if the table doesn't have any particular field in TaxonWorks, we have data attributes. We can customize list of the fields, could be added to any tables in the database. We have number identifiers, global identifiers, local identifiers, confidence levels, citations, depictions, tags, and many other things. And this is just one example. And you can see those radial annotators virtually next to each object, next to the taxon name relationship, references, so you can open those easily and add any comments about the object. Edit taxon names, I won't stop too much on that, but basic information is very limited, just 3 fields, names, parent, and rank. The rest is optional, but highly desirable, so we add this information as well. Author, status based on the nominantology we design also in our group. So you can go just say that the name is nomen nudum, but you can be more precise. It's nomen nudum because certain things is missing in the original publication. Original combination, type information, relationship, also based on the nomen. So also hierarchical structure. You can say the name is synonym, but you could be a more specific subjective synonym, and some other more detailed information. Bibliography based on the BibTeX, so we split the text, and that's not from Sistema Dipterorum, but from another project, but you can attach PDF files. If you have PDF, you can see it inside of the system, or you can download the file. Getting new source to the database as simple as just adding DOI reference, and we call cross-ref service and split reference to individual field in BibTeX format. So yeah, it's very, very friendly. Filters, we have a lot of filters in the database. This is filter nomenclature. In this case, I just search by one parameter, get a number of names. One thing about TaxonWorks, I can send results of one filter to another filter. So let's say I want to find all bibliographic references for those taxon names. I can do this through this interface and get the list of sources. One thing I didn't mention, getting data out of the database, we try to do it from the very beginning. We think not about how to get data to the database, but how to extract the data. So each filter has download options and multiple ways to get it. CSV, BibTeX, and we also provide specific journal formatting. You can generate paper catalog from the data, almost publication ready, with basically all the information summarized. And we have public interfaces. Again, I didn't do any fancy stuff, just one single search box, but it's already searchable. You can get access to it and try it. And you can get all the information about the species summarized on the single page. Some basic statistics, 248,000 names, 40,000 sources. And again, as I said, data accessibility is an important part of any database, how you can get data out, full project dump, individual tables, API access to all models in the database. Nomenclature goes to catalog of life. Although we don't have a production database for Systema Dictatorum, but we use this as a pipeline to getting data to catalog of life now. Bibliography, specimen data in Darwin Core, and we have matrices which could be used for interactive keys. We also have Nexus, XML, TNT outputs. With that, I would thank you. If I have time for questions, I don't know.
So we do have a couple of minutes for questions. Please feel free to come up to the mic if you have any. And thank you again for that talk. How did people find out more?
Yeah, I will have a demo after lunch, and we have some additional information. We are on the Gitter, we are on GitHub, we have documentation section, and we have events about TaxonWorks. We have a weekly event on each Wednesday, and we have annual event TaxonWorks Together in May. And of course, you can talk to me or Debbie Paul.
Oh, do you have one more question? And I guess I have one more question that people might find interesting is how do you get involved with TaxonWorks?
Well, we had several projects developed before TaxonWorks. We had original species files originally for Toptera. I had developed 3i database for my group of interest, leafhoppers and hemipterans. And Matt Yoder, who developed a system for Hymenoptera. So we ended up in the same group and decided that we will channel all our effort into development of single project instead of maintaining several competing projects. Please.
Oh, sorry. So another thing you guys can do for those of you who just want to test it out and see what's possible, anybody can have a sandbox. Come talk to Dmitry or me. You can play with it to your heart's content.
Yeah.
You can't hurt it, can't bust it, can't do anything. So paleontologists have adopted it. There's fish people who are using it, people who do their own marine research. They're managing their own research data in this. So there are collections level people managing their data. The insect collection has over 1 million records in it. There are, besides, I just wanted to give, beyond insects, there's also paleo. There's plant people investigating this and working with the implementation of, sorry for the buzzword, RCC5 implementation in order to be able to understand taxon concepts and how they change through time and track that within your database. And we link to ontologies and Dimitri mentioned Nomen, but we have ontologies like the Hymenoptera ontology, but Pato, Envo, many of you are familiar with these. And in TaxonWorks, we actually link to those inside the database. So there's some things, if you want to see how we've done that, we also encourage you to join us in this mode of building open source software where we can use the kind of tools that for each other. So we built a GitHub tool, or GBIF tool, sorry, it gets the data from GBIF about your specimen record. What does GBIF assert about your specimen record? You don't have to go out and get that data from GBIF anymore. If you use our system, it comes back in the system already for you so you can see how GBIF sees your record. So talk to us if you want to experience TaxonWorks.
Awesome. Thank you so much. Let's give another hand for Dimitri. And our next speaker is Robert Kuby, and he'll be talking about migrating to collection management systems, CMSs, during a global pandemic, lessons learned from the Royal Botanic Garden, Edinburgh.
Thank you. I love coming to these conferences. I love attending the talks. I love the interactions. I love learning new techniques and new ideas. What I don't like is speaking myself. But my institution has a rule, and the rule is if you attend, you speak. So I'm here, and then what do I speak about? The logical thing is to talk about what's been occupying my life for the last 4 years, which is a migration of one existing collection management system into 2 new collection management systems. I hope this warts and all talk will provide insights on how to do this, as well as how not to do it. Because if you do manage a CMS, you will be doing it sooner or later. Nothing lasts forever. I'm going to give an introduction to the Botanic Gardens. I'm going to go through the previous collection management system. And then I'm going to talk about the living collections management system that we currently have and the preserved collections management system we currently have. Introduction to the gardens. We are Botanic Garden in Scotland. We are based at 4 sites across Scotland. We have Logan in the southwest, which is sits on the Gulf Stream and is we call it tropical. After being here for a few days, it's not tropical. It is a warmer for Scotland garden. We've got Benmore on the west coast. It is wet and high rainfall, and it's also on a slope like that. We've got Doik down in the borders, which is cold for us, but again, it's not half as cold as some of the Midwest of the United States or the Russian gardens. It's cold for Scotland. And we've got the main garden in Inverleith in the centre of Edinburgh. And inside the garden in Edinburgh, we have a herbarium inside the garden. It's on the top 2 floors of this white building here, 1960s building, which has a leaking roof and leaking air conditioning system and all kinds of 1960s issues with the building itself. But it is a nice building in the middle of a nice garden. The garden itself currently has about 64,000 plants growing in it, but we have been active since 1670 as a garden within Edinburgh, within the city of Edinburgh. And so there are over 100,000 living collection accessions from those last 350 years. In the herbarium, we have about 3 million specimens. We don't know exactly because we are in the process of finding out, because we're in the process of digitizing our herbarium. We are digitizing it in-house, using a small team of digitizers based within the herbarium itself. There they are, you can see more of the electric desks and the light boxes. It allows us we haven't had any major funding lumps, millions of pounds from government. We've had a steady stream of small amounts, and this gives us the flexibility to increase or decrease our digitization according to the current funding stream. It also allows us, because it's based within the herbarium, it allows us to do some curation and collections care at the same time, which we think is important. Okay. previous collections management systems. Kremenko. Back in 1967, the RBGE had a living collections database, which was based on the Kremenko system, with a massive 5 megabytes of hard disk, and we were allowed access to it for 1 week per year. During that week, we had to produce all the bed lists and collection lists for the garden. We left that in 92 and moved to, moved to BG Base, which was a PC-based collections management system. And then in 1998, we started a database for herbarium using BG Base. But what happened was, over time, other requirements came on board, things like a dam. And while we argued about what to put in the dam, was it stuff that was going out for publication? Was it internal collections images? Well, we're still arguing about that. We also got involved with ArcGIS, but we had nobody on staff to do it. And we also got involved with some of the new databases like Silica Preserve database, the material in silica. And none of this was able to fit into our current collections management system. We also had more requirements within the herbarium. We had a PADME database, which is a cradle-to-grave cradle-to-grave system where specimens collected go right through to publications of floras and checklists. It manages the whole production of the whole production of monographs and floras and checklists from collections through to end. This was running so the flora of Nepal and a few other projects were using this, and it was running alongside our collections management system and was causing internal angst about some people were databasing in one system and other people were databasing in the collections management system. It was causing problems. Similar idea with Brahms. We had certain teams who were working in Brahms, and then because the rest of their team were working in Brahms across a number of institutions, and were then giving us exports, which we were then having to put into our collections management system. And BG Base was a black box. We couldn't really put data into it particularly easily. And in order to get data out to our online catalogues, we're having to export it to a MySQL database anyway. So what we were after was a database that had some of these modern linkages, wasn't just a black box that we couldn't do anything with. So we, I've gone the wrong way now. No, there we go. We set up a requirements matrix and started to look at procurement exercise and got involved in all of that. And it's way too boring and painful to go into here. It is horrible, frankly. But we came to a decision at the end of it, and the decision was that we were going to go to IRIS-BG for the living collection and particularly specify 7 for the area. Okay, let's go on to living collections to start with. To start with living collections, the first thing we did was to get a dedicated migrations officer on the staff. Shit. Sorry, I've just seen the time. Was to get a dedicated migrations officer on the staff and short-term contract, and that really, really helped, and that was great because it took some weight off some of the existing people. Not many of you will know IRIS in here. IRIS is a bespoke database for managing living collections within Botanic Gardens. And because of the time, I'm going to just jump straight over why we chose IRIS, but to say we did. The successes were, we managed to migrate into IRIS in 7 days. And the reason was there was a proven migration pathway. Two of the other institutions in the UK, National Botanic Garden of Wales and the University Botanic Garden Cambridge, had already done that migration. So it was very easy for our data to go through their migration process. We paid for it to be done by the company itself, and we were down for about 7 days. That was the amount of time it took to upgrade the database and get it back to us and get it live again. And then once we got it live again, we could do the testing, the training, and all the other things. And we had a program and a person in place to do that. Hort staff are notoriously adverse to change. They grow plants over long periods of time. They don't like change. And we've been using VGBase for 25 years, and some of them have built their career on VGBase, and they did not want to change. But a couple of early wins of mapping and handheld devices meant that we got easy wins and got ahead. But one of the things that happened was the pandemic came, and everybody had a lot more cash to spare because they weren't going out drinking and going out to parties. And so they all the Hort staff bought themselves posh new iPhones. And at the same time, the RBGE realized they also had to communicate with their staff. So they gave everybody a really cheap Android phone. And when I say really cheap, I mean really cheap Android phone. And then I gave everybody nice posh handheld devices, barcode readers like you get in supermarkets. And suddenly the Hort staff had 3 devices that they were trying to go out with, as well as spades, forks, and guess which one got left on the desks? It was my heavy handheld device. They took their own phones and took the work phones and left my devices on their desks. So that was a failure. The second thing was the mapping. Suddenly you could see where things were, and it was great. But it also meant that you could see where things were. And suddenly the Hort staff could see where things were and realized that they hadn't updated their records. And things that were meant to be in bed A11 were way over the other side of the garden. And it was great for data control and great for data quality, but it became a real problem for the Hort staff because their managers could see how much record work they'd done, and they got really upset by that. Oh God, right now, I'm sorry. Migrating the preserved collections. This decision was a bit harder because we hadn't got a decision matrix in place. And so we had a decision matrix, but we didn't have a migration pathway. So we ended up trying to migrate and then rolling back and trying again and rolling back again. And it was a heavy, it took a long time, and it was an emotional journey, partly because the existing database member, the BG-based developer, was based in the garden, and it was very emotional for senior staff who were his friends to be changing database away from him, and it caused an enormous amount of emotional angst within the collection. The other issue was we're trying to work from home, and we were providing test data in spreadsheets, new data entry via CMSs, feedback forms, Microsoft Teams. We couldn't do training, we couldn't do development. It just, one laptop screen with all of this on was just too much. And the cultivated specimens became a problem. We'd had one database before for the two living collections and preserved collections. Now we had 2 databases, and trying to link between the 2 was a real problem.
I don't think we have internet connection.
It's okay, I didn't plan it to be a video, so I'm really pleased we don't. We had the current problems of you all recognize from Herbaria, multi-sheet specimens, and multi-specimens on sheets, and we had the new problems of managing destructive samples, which is only getting more and more problematic. And then we also had the problem of having, with a new database, we then had to find a way of remapping all of our existing relationships, all of our existing data relationships. Flip's sake, what? Sorry. Thank you.
Awesome. Thank you so much for that. We don't have time for questions at the moment, but our next speaker is Alan Payton. Lessons learned from implementing a new collection management system, a case study from RBGQ UK.
Thank you. So I just want to thank my co-authors, some of the Q implementation team, and Evgeny from Earthcape, who's wearing a subtly branded t-shirt at the back. And I should stand closer to the microphone so you can hear me. And there's a seat at the front. So I'm going to, for those of you waiting to hear about the details of collection management systems technically and collection management, generally you're going to be disappointed because I'm going to talk about the people stuff and the relationship stuff. So if you're waiting for that, you're probably going to be disappointed. And one of the key lessons is that, you know, this is a journey. People get taken out of their comfort zone, but we have to get the message. It will be all right in the end. We will get to a better place. A bit like this talk, maybe. Okay. In the beginning, it was chaos, and out of chaos came more chaos. We started off with at least 8 collection management systems, maybe 9. Some of them had 2. Researchers had their own databases, began as standards, but actually researchers don't trust researchers with standards. They'll do their own thing anyway. But that wasn't the biggest problem. The biggest problem was that data got lost. People basically took lots of effort and flushed it down the great toilet in the sky, and huge amounts of effort just disappeared because it wasn't an institutional system. So we ended up with a mess, and the only good news was that everybody knew it wasn't good. So from that position, you can only really go upwards. So this is where we're aiming. Everything in one system, everything connected in a stable, modern system. That's the thing. You don't want people to forget that. You may have problems along the way, but that's what we're aiming for. It reduces risk. It helps you comply with this ever-changing and ever more increasingly complex legal system that we live in around the world. And our developers might get to do what we want them to do rather than firefighting constantly and trying to keep collapsing systems running. So that's all the benefits. So we had tried this before, about 5 years previously to this exercise, and it didn't work. We didn't get funding after doing quite a bit of work. And why not? Well, we had support from management, but I don't think we had engagement. And how do you tell the difference? So support is senior managers smile at you, say, hey, jolly good, carry on. Engagement is they look at you and listen and say, ask you challenging questions and answer emails and show up at meetings when you want them to show up. And that's really important because not only do you need staff time and get people to buy in and make changes to the job description, it's also because the project will end and long term it's got to continue. So you've got to set up the expectation of what happens next. And that's really difficult to do without the buy-in in the long-term picture. You can't just think of this as a project. It's got to be a new norm in the long run. So planning. We asked a lot of people, we went around and people said, oh, it takes about 18 months. And I'm thinking, 18 months, they're mad, what are we doing? We'll do it in about 6. So when we started project to when we got the first tender finished, it took us 18 months, pretty much. Actually, it probably took us longer than 18 months because we did a bit of planning before doing the 18 months. But we got there, and the process is assisted by starting early, getting specialists in, like business analysts and program managers, but it's not just getting them in, it's actually embedding them in the team so they become part of the staff. So you kind of set up this close team which can embed itself within the institution, because you're going to all sorts of different collections in different places. So they need to be known, you need to have a profile in order to talk to people and get to know people. So it's really important. What we did was we were looking at what we currently did, but also what are the key requirements that we didn't have. We also had to cover things like what wasn't in scope and be quite explicit about the sorts of things that weren't in scope. And the Spectrum standard by the Collection Trust is, for those who don't know, is basically a kind of guidebook to best practice. It's not brilliant for natural science collections because it was developed from a cultural background, but what it does do is it gives you a checklist of things you need to think about, and that kind of keeps you in the straight and narrow as to what has to be in it, if you like. And the project manager just keeping things on track, working hard, and keeping that engagement with stakeholders going all the way through the project. Collaboration with EarthCape. So we've got a variety of collections going from the kind of very museumy, ethnographic type collection to the seed collection, which is almost in some areas more like a laboratory management system. So getting one system to fit off a shelf to fit all of that is not really going to be likely. So we try to find a collaborator to work with us to understand all these differences. And we had a tender process, which EarthCape won. Part of the reason they won it was because they appealed both to the developers, but also to the staff, the user interface and that kind of thing. And we have truly collaborative development. We share tools, we share constant communication. And I think it's going quite well, but if anybody sees Ev, don't tell him, because I want to keep him on his toes and, you know, don't want him thinking he's got too much of an easy life. Okay. So, beginning of lessons. I think we probably initially underestimated the amount of data cleaning that had to be done, and the testing and the training. And bear in mind, with people testing, don't test. It's the first time they've ever tested. We don't, you know, that's a complete ball change for them, a lot of people. It takes time. It's more impactful in smaller collections, because if you've got a big team, you can kind of spread the share about. If you've only got 3 curators in a particular collection, that's quite heavy on them. So that takes longer than you think it's going to take in the smaller collections. And again, about trying to talk early to people, like 6 months before we move into implementation, beginning to get an idea of what the system looks like and what the requirements are, but also thinking about what the change is going to look like and how they can benefit from it. Okay. Training, Olivia gave a nice little talk, she's at the back, on training. Like all kind of project managements, you need kind of one source of truth about things. So although at first approximation, no one reads a training manual, it's really important to have it, because that gives you all the information which you can then take out and do targeted training, do general introductory training, because it's all there in one place. I quite like reading training manuals, but I'm a sad but it's, for sad gets, it's great. You can go and look at this, you can look at the trading manual. Okay, what we didn't get right, or we maybe haven't quite worked out. Testing systems is alien to a lot of curators, and it takes time. And people think differently about this kind of thing. Some people want to see the whole thing, other people want to do bit by bit. Developers want to do bit by bit. They already know the whole thing, and they say, well, you can't do this bit until you've done this bit, so they take it through step by step. And the curators are just like, no, I want to see the whole thing. And I don't think we ever got that right yet. I think if we did the seed again, we'd go back and say, here's the big picture and here's the little bits, and we're going to do the little bits at a time, and actually explain that picture to them in more detail. We kind of jumped in a bit too early. Regression testing, I didn't know what regression testing was until we did Earthgate. It was a complete surprise to me. And I think sometimes we were maybe a bit too quick, and that relates to the previous point that you start, but it's not the end of the process. It's going to go on. We're going to be reiterating this project and getting it closer and closer to the state you want. So it's not all finished. And you're balancing that against deadlines. Right? Deadlines are important because if you can't finish on time, you're not going to get the next slot of money to do the next bit. So there are constraints externally. And finally, coming back to the beginning, planning for post-project, really important. You have to kind of think, right, the managers don't like surprises. Warn them early that this is going to cost. Will it work? I don't know yet, but I know the managers know the cost, and I know they're supportive. Whether we get the money is ask me in 2 years. It's kind of beyond our control. Lots of external factors like government spending reviews, political change, all that. But at least we're prepared. Thank you.
Oops. Thank you so much for that. Do we have any questions from the audience or on the chat? If you do have questions, please feel free to come up to the microphone. Okay, so if there aren't any questions at the moment, let's give another round of applause. And our next speaker will be Lisa Brain from Disco Flanders, and she'll be talking on Disco Flanders and ILVO CMS, unlocking and enhancing the management of natural science collections in Belgian research institutes. Thank you.
So hello, I am Lieselot, and I work for the Flanders Research Institute for Agriculture, Fisheries and Food. And today I would like to tell you about how we are trying to unlock our natural science collections. And since collection management has not been or is not our main business, how we are trying to improve that. First, let me introduce or reintroduce you to DISCO. It's a fun acronym for Distributed System of Scientific Collections. It's a European research infrastructure with the aim to digitally unify all European natural science collections to make the collections more visible and used. But to get there, all the collections need to become fair first. So, in Flanders, the northern part of Belgium, for those of you who might not know, we have DISCO Flanders. It's a consortium of 14 institutes who are together trying to make the collections in Flanders ready to be integrated into the DISCO Europe infrastructure. So ILVO, the Flanders Research Institute for Agriculture, Fisheries and Food, is where I work. And there we are mainly doing research into the sustainability of agriculture, fisheries, and the agri-food sectors, as the name implies. We have about 15 very diverse collections, but most of them are very small. In total, we have about 558,000 objects, but almost 95% of those are marine fish otoliths, so one collection. These are used for age determination, and by that to make fish stock assessments of commercially important species. All the other collections are fairly small. We have insects, living plants, sediment, DNA, a bit of everything. So up until now, or still today, all collection data is being is being kept in Excel files. These files are on local computers of the researchers working with them. So as you can imagine, not ideal. So we started thinking about how we needed a collection management system to improve this. And first we looked around at the systems that are available, at one that could give us a very quick and easy solution. We didn't really find one that could help us, that could give us a simple and quick solution. So as we have an in-house database framework already for other applications, so we have the code, we decided to just try to make our own simple collection management system. And that is how Ilvo CMS was born. Bit of technical stuff. It's an ASP.NET web application based on a normalized Microsoft SQL relational database. It has dynamic web pages, which was very important because we have very diverse collections. So for each collection, we needed collection-specific fields, and a lot of them, unfortunately. So now I'll show you a bit how it looks like. So this is the main screen. And if you click on the left upper icon, you get the different pages that you can go to. The most important one of the most important ones, is the collection management itself. So there you can see all the collections that are in the system. Here you can add new ones or edit the ones that are in it. But most importantly, with the show property function, you can select which properties or fields which will or will not be shown for that specific collection in the screen where you add the items. Then you can also link species to specific collections so that you don't get the whole list of species when you want to add one. Then secondly, the security. Here you can add or edit the people who can go into the system, and you can give them specific roles based on what they can or cannot do or see. Next, as I said, we have a lot of collection-specific fields or properties, and these we try to give them all lists, so to minimize the spelling errors or just a lot of words to describe the same thing. So we made a lot of lists. For example, for DNA extraction kit, we have this list, but you can also link the lists to the collection. So like this, you can see for each collection which terms are in the list that they can choose from. You will see later. Then, yeah, you can have an overview of all the species in the database. And then we go back to the main screen. It shows it's by category to, because the bosses wanted that. Then you can see per category what kind of collections that you have. So for botany, we have, for example, seeds. When you go to the items in the seed collection, you get this nice overview. You can also filter and search through these things. You can add then documents, PDFs, or pictures. When you want to add a new item, this is what you will see, kind of. And as I said, most of these will be based on lists. For example, like this, which, like I showed, you can manage yourself. Well, not everyone, but the people with the authority. Then dates are also done like this, so that they are all in the same format. Next, for the collection-specific properties, there will be an extra grouping of fields like this, and most collections have like the specific ones. Then you can also add references to other databases, external or internal ones, GenBank, for example, or whatever you want. You can add relationships to other items in the collection. Might be useful for like plants and seeds, like what we have. And then you can also add transactions, for example, loans, or when a whole collection dies. I don't know, could happen. The future goals of the Institute, well, in this, for this thing, is the further development and implementation of the ILVO collection management system. Now there's only one collection in it because data cleaning takes a lot of time, apparently. Then we would also like to try and implement 3D images of certain collections and develop a website to make our collections visible for the outside world. The take-home message I want to give is that the collection management system for us as a small research institute will greatly improve the management, organization, accessibility, and exchangeability of our collections, and so increase their scientific value. And also that through projects like DISCO Flanders, we could get temporary funding and collaboration with other institutes, which made it possible for us to contribute to the global natural science collections as well. Thank you.
Awesome. Thank you so much for that talk. Do we have any questions in the audience? Do we have any questions online? Okay. I'll wait a couple more seconds. We are running quite a bit ahead of schedule, so I'm sorry about that. But yeah, so let's give another round of applause for Lisa. And we will move on to our next talk of the day. This is by Marla Spencer, who will be speaking on pioneering museum data transformation, unifying legacy systems, and enhancing data integrity.
Hello, thank you very much for the introduction, and it's a pleasure to be here. I just want to apologize in advance for reading from notes. It just makes me feel more comfortable. So, all right, so we're going to jump in. All right, so the Natural History Museum houses over 80 million specimens, with over 9 million specimen records currently within our CMS. We're facing some deeply embedded historical data challenges that date back to when our collection data was first consolidated from various sources, like card index boxes, Excel sheets, and databases, into our initial CMS. This was a significant achievement at the time, but differing requirements for similar concepts created divisions across departments, effectively leading to the development of 5 distinct siloed data models coexisting within a single CMS. Fields representing the same concepts were named differently across departments, making it difficult to manage the data consistently. What was intended to be a unified system became fragmented, with each department using it in its own unique way. Over the years, we've made some considerable efforts to harmonize these fields, improving the data with each iteration. However, one of the biggest obstacles that we faced was our inability to gain a comprehensive view of our data and its issues until we started uploading data dumps into the Amazon Web Service, AWS. This allowed us to query all of our data across all departments, across all fields in seconds, providing a comprehensive view that was previously unattainable. And while our CMS is about managing the collections first and foremost, externally, there's a growing need for standardization as we now regularly publish and share information for purposes we never anticipated. Our CMS was initially designed as a digital register to record objects in detail, but its role has evolved. It's no longer just about recording details, it's about ensuring our data is usable, shareable, and standardized using FAIR principles. So I'm part of the Recode project team, which includes 11 core members and 5 technical advisors, and our collective goal is to create a new CMS. Our team's diverse expertise ensures that we have the right skills to thoroughly understand our data and our users' needs and translate these into a new system. As the data analyst, my role involves migrating our data to the new system, but my primary responsibility is to analyze and prepare our existing data, setting the foundation for the entire workflow. Why are we developing a new CMS? The museum has an ambitious digital strategy aimed at supporting global research and improving the management of natural history collections. To achieve these goals, we need a CMS that is flexible, user-friendly, but one that is also performant, robust, and lets us work with our data at scale. So today, my goal is to share the experience and the knowledge that we've gained throughout the data profiling process so far. And I'd also like to highlight some of the presentations from my other Recode colleagues who also addressed some of the challenges that we face. So yesterday, Ben spoke about the data model in the SIM 25 session. Yuta presented in the controlled vocabulary session. And Steen provided a project overview in the SIM 01 session. So, the first step in this whole process was getting to know our data better. So my work is crucial for understanding our data. So what does our data look like? What is its structure? How many fields are there? What are the data types of those fields? Do we have a definition for what that data field is? How do users actually use that field? This is very important. Collaboration with stakeholders and creating documentation for each discrete data category. And what we found out was we have a lot of data. So currently we have 263 million records. That's 12 terabytes of data. Most of this is audit records, so which track all inserted and modified records and their timestamp. But excluding those, we have over 26 million records within discrete concepts like taxonomy, multimedia, geography, people, and organization. Of the 26 million records, 9 million are specimen records. So the 263 million records were spread across 8,175 fields. This is a significant amount of data to move into a new system. So our first step was to assess whether all of it needed to be migrated. We established clear criteria for reviewing and filtering the data during the initial phase of the migration pipeline. This process identified fields with no future value, such as duplicate data or system-generated fields, fields related to organizational processes and permissions, allowing us to remove them before the complex transformation and mapping stages. After several rounds of reviewing and filtering fields in the data profiling stages, we systematically reduced the number of fields from over 8,000 to just over 3,000. That is a 63% reduction. So imagine this is trimming down the columns of a spreadsheet from 8,000 to 3,000. So this work was a significant achievement, and it was vital for reducing the scope and complexity of the migration and the data modeling. And this translated into making the data more manageable to handle, and it resulted in substantial time savings. However, the 63% reduction has only been possible through the effective use of governance structures like collections committee and stakeholder groups, as well as the trust that we've earned from our users. To further reduce the amount of data being migrated, we analyzed records to identify those not linked to others, indicating that they were unused or unreferenced. We examined a subset of 18 million records from 9 discrete categories, such as taxonomy and multimedia. The blue represents the total records, while the red shows the unlinked records. We found that over 4.2 million records were unlinked. After an investigation by our data management team, omitting these resulted in a 23% reduction. So think of this as reducing the number of rows in a spreadsheet. To continue to get to know our data better, we plotted our specimen records across 5 different departments, each represented by a different color. And while the axes are not readable due to the zoomed out nature, the focus here is on the big picture of user behavior. The bottom axis represents the individual fields we use to define a specimen. And the graph reveals that many fields are used by multiple departments, so you can see that here, while others are unique to just one. And so our challenge was to delve deeper into this and untangle which fields are used by each department and identify the shared fields. So next we analyze fields used by the specimen records, grouping them by concept, such as notes, hazards, determination, and registration. These groups are represented by the different colors on the chart. And although initially set up for specific disciplines like mineralogy, entomology, or paleo, many of these fields became necessary across departments and were repurposed for shared use. For instance, this large bar for entomology includes the field for the specimen barcodes. So originally created only for entomology, this field is now used by all departments. The large numbers that you see here are driven by the extensive work of the NHM digitization team, which accelerates the creation of specimen records. So using this field group approach, we plotted the fields across departments. And while the details are hard to see, the key takeaway is the overall pattern. Each color represents a field group, showing that each department has unique requirements. However, we found commonalities. Some fields, though named differently, were the same concept and could be harmonized. Conversely, some shared fields were used differently, requiring a split. This work and these insights are useful because it informs the design of both the migration pipeline and the future data model. So given the descriptive nature of our data, it's challenging to dictate standardized vocabularies. AI tools like AWS SageMaker can help identify similarities and differences, aiding in the merging or splitting of fields. Overall, our analysis allowed us to ask critical questions like identifying the unique combination of populated fields that matter. It provided the insights needed to make informed decisions, highlighting that fields should be based on the nature of the data, not the department. So our focus is shifting to what the object is, aligning with the global standards in the biodiversity information community. So one final topic is data cleaning. And while it's essential, the real challenge lies in breaking down the problem beforehand. Understanding the structure before starting the cleaning process was crucial, requiring significant effort and far more work than we realized. So we prioritized our data cleaning activities into three. So firstly is pre-migration. These are critical tasks that must happen first. So quality checks that are built into the early stages of our migration pipeline help identify and divert problematic records, allowing us to focus our efforts on those that are structurally incompatible with the new system. So fixing these issues was essential, and this is where we put the bulk of our effort and resources. Secondly, the second phase was during migration. So these are automated tasks, and I'll come back to that in just a moment. And finally, post-migration. So this requires stakeholder involvement. These are resource intensive and require discipline-specific knowledge to address non-critical widespread data quality improvements, such as semantic deduplication. So this is a high-level diagram showing the processes and the services involved in our migration pipeline so far. So we use an ETL process to extract, transform, and load in AWS before moving our data into Doxis, which is our new CMS system. In addition to identifying problematic records, the pipeline can also apply automated methods to perform straightforward data cleaning tasks, such as standardizing inconsistent terms, so country names spelled various different ways, reformatting dates, and standardizing letter casing. So this process is repeated with a tailored to-do list for each iteration, allowing us to configure specific instructions for different data fields. In the future, we would like to use or utilize SageMaker AI to help with this process. And eventually, we aim to utilize external APIs to map data to external vocabularies, improving our data, keeping it up to date, and thus reducing the pressure on our curators. So I'm very quickly running out of time, so I'm only going to go read a couple of these. But lessons learned, very importantly, this whole process has required us to take a step back to thoroughly understand and realign our data. Each iteration has enhanced the quality and integrity of our collection data, and Recode is a significant milestone in this ongoing journey. Very importantly, we now, or maybe most importantly, is we now know we need to establish an annual plan to tidy up and address known issues. So this is something going forward we will need to take on. And finally, I just want to thank my colleagues who are all doing incredible work, and thank you all for listening. I know I probably don't have much time for questions, but please feel free to connect, to chat, because this is complex and difficult, and I would be really happy to hear your thoughts and questions. So thank you all very much.
We have time for like one question. And if nobody's going to hop on it, I will so make a decision quickly if you have a question. Okay. I have a question. How easy is it to talk to the people who are developing the pipeline? I do engineering in AWS, and I'm interested like what they're doing.
Okay.
Yeah.
So Sarah Vincent, who I'm sure many of you know, she's my line manager. She is the one who is orchestrating, creating, and building that pipeline, so I can connect you.
Yeah. Awesome. Thank you. Any other questions? Perfect. Well, thank you all so much for attending. Let's give another big hand for everybody. We ran about 15 minutes early, so 15 minutes back into your day. And I hope you all have a wonderful lunchtime.